You know, Mr. Call Me, and I'm going to take you through how to do solution stoichiometry quick. Hopefully I can get it done in a short period of time here. But we need to think about what stoichiometry looked like when it was mass-to-mass stoichiometry. Remember, in February, we had a flowchart that looked like this, where you convert from mass to moles, and then you go from moles to moles, and then finally from moles to mass. This is the three-step stoichiometry that we learned in February. Each step of the way you use a conversion factor. In order to convert from mass to moles, you use the molar mass. In order to convert from moles to moles, you use the mole ratio. In order to convert from moles to mass, once again you use a molar mass, but of the new substance. Now this is mass-to-mass stoichiometry. And today we're going to talk about solution stoichiometry, where we're going to add a little twist, something new here. We're going to add volume to this idea of stoichiometry. Now volume could be a starting number, or it could be a starting unit, or it could be an ending unit. In fact, I'm going to write this underneath so I have more room. So let me erase this. Right down here. Volume goes down here, or volume could go down here. So we could use volume as a starting number or unit, and we could use volume as an ending unit. Scroll up here. The conversion factor you use to convert from volume to moles is that new conversion factor, molarity, that we learned about last week. Remember, molarity is equal to moles over liters, and anything that has two units in it, like this one, moles and liters, just like molar mass has grams over mole, has two units. Well, since it has two units, we can use it as a conversion factor to convert from one unit to the next. And molarity is no different. You can use it to convert from volume to moles, or if you know the moles, you can use it to convert from moles to volume. And so I'm going to take you through a couple of problems here today. But before we do that, let's talk about the situation or the process here. The process is, first, you need to figure out where you start, what unit you start with. And you could start with either grams or liters. You could start with grams or liters. Now in mass-to-mass stoichiometry, we only started with grams, but now we're using solutions, you could start with liters. 2, you end your possible endings are also grams or liters. Let's scroll back up. I mean, if you start right here, put mass, you start with mass, and you convert from mass to volume, that's one type of problem. Or you could start with mass and convert to mass. Now, we won't do those types of problems because we've already done those, tons in February. So, really, I'm only narrowing it down to three types of problems. You go from mass to volume, like we already talked about. We can go from volume to mass, or you could do volume to volume. Either way, you have two options for what you start with, and you have two options for what you end with. You just have to look at the problem to figure out, identify, to problem solve, and figure out what unit you start with, what unit are you given, and what unit are you supposed to end with. And then finally, number 3 here is that in the solution stoichiometry, as in all stoichiometry, all stoich always has a mole ratio. Always. You never have stoichiometry without a mole ratio. This spot right here in the middle, this mole to mole ratio is always going to be the second step in these problems. So I'm going to show you what I call molarity first step or molarity last step problems, because that's the two different ways that these could possibly show themselves. This one is a molarity first step. Let's take a look at what we're given. We're given 25 milliliters of 0.5 molar NaOH. Next, mixed with a solution of FeCl2, and you're going to produce a precipitate of FeOH2. How many grams of FeOH2 are produced? Well, this is a molarity first step. So what you want to do is you take what we're given in the problem is either liters or grams. You either start with liters or grams. Well, what do we have? We don't have grams. We have milliliters, which in a sense is liters. You can convert milliliters to liters by moving the decimal over 3 to the left. 0.0250 liters is what you have to start. And your first move, like I showed you in this last step, your first move is to go from volume to moles. Go volume to moles using molarity. So, if I know the molarity, which is right after it, it's 0.500 molar. Remember, 0.500 molar means that there's 0.500 moles in every 1 liter. With that in mind, I can use that information to solve for moles of NaOH, because I know the molarity is 0.500, that's 0.500 moles over 1 liter, so liters cancel. Next step then is that step that's in every time you do stoichiometry. It's the mole to mole step. Moles of known on the bottom, and that happens to be NaOH. The moles of NaOH go on the bottom, and moles of what I'm looking for, which is FeOH2, go on the top. Now I get these numbers from the balanced chemical reaction. I got 2 NaOHs and only 1 FeOH2, so I go 1 on top, 2 on the bottom. And the last thing you do is solve or answer the question. The question is, how many grams, I'll circle it here, how many grams of FeOH2 are produced? Well, that's just like a normal mass-to-mass stoichiometry problem. Your last step is to go from moles of FeOH2 to grams of FeOH2. And you use a periodic table to find that out. So I'm going to use my periodic table. I'll add it up here quick. And I get 89.86, and that goes in the top. Oh, 86, not 68. 86, and that goes in the top, because that's how many grams there are in 1 mole. So the only thing I have left here is grams of FeOH2, and now I just need to total this up into my calculator. And if I take 0.025 times 0.500 and then divide by 2 and then multiply by 89.86, I get an answer of 0.5616. Now I added a ton of significant figures, so I'm going to round that to the least number of significant figures as my original numbers, which is going to be 3 sig figs, so it rounds to 0.562 grams, and that's my answer. This is a molarity first step, where I use the liters given and the molarity to calculate moles, and then from there I just do mole to mole and finally mole to mass. Solve. Now the second type of problem is the molarity last step. So it could be either molarity first step or molarity last step. This molarity last step problem is a little bit trickier, but you started out the same way you would a mass-to-mass stoichiometry problem, because you're given 25 grams here. Remember, you got 2 options. You're given grams or you're given liters. You don't know the liters, how many liters. In fact, you're not given any other number besides the molarity. Now, you want to make sure you know this. You never, ever, ever start with a molarity. Your starting number should never be molarity. It should be either grams or liters. Now, we've got grams of FeCl2 here. Now, sorry, I can't type in subscripts on this application, so I just have to type big 2's, but really you need to know that the Cl2 is actually small. Anyway, first step in mass-to-mass stoichiometry is you take the grams and you put grams of FeCl2 on the bottom and moles of FeCl2 on top. And you want to figure out how many grams there are in 1 mole. And according to my calculations, there are 126.75 grams of FeCl2 for every 1 mole. So that's the first step. Second step, every stoichiometry problem is the same. Second step is the mole-to-mole ratio. Moles of FeCl2 on the bottom, and the moles of what I'm looking for, which is NaOH. That's my unknown. Now I use the mole to mole ratio. In the problem, you got 2 moles of NaOH for every 1 mole of FeCl2. And I finished this off with the molarity last. This is what I call the molarity last step problem. It's because I want moles of NaOH down here, and I want liters of NaOH on top. Now this is a molarity, but it's upside down. Remember, molarity is normally moles over liters, but I can flip it around to become liters over moles so that I can get the moles to cancel, leaving behind my liters. Just remember that if you flip it upside down, the number of molarity goes where the moles are. So 3.0 moles per liter gets flipped around to be 1 liter over 3.0 moles. So that's what I'm going to do, 1 liter over 3.0 moles. And now I push this in my calculator and see what I get. If I take 25 divided by 126.75, multiply by 2, and then divide by 3, I will get a final answer of 0.1315, or 13149. But I'm going to round that to 2 significant figures. The reason being is I've got 2 measured values in my starting number, or in my starting question, 3.0 molar and 25.0 liters. There's 25.0 grams. Normally you round it to the 25.0, or the 3 significant figures. But in solution stoichiometry problems, you have 2 measured values. The molarity counts as a measured value. And thus you have to round to the least number of significant figures of the measured values in the problem. And so this number is going to round to 0.13 because it reflects the 2 significant figures right up here from the NaOH. So the final answer is 0.13 liters. And that's your answer, 0.13 liters. So hopefully it's a little bit more clear. You utilize this little video as a way to help you review solution stoichiometry, or if you were gone on Tuesday, May 6th, you should check out this tutorial as an example of what we did in class. But that's about it. If you have any questions, feel free to stop in and get your questions answered. I'll be more than happy to do that. So, well, that's it for now. Catch you later.